Chapter 5, Part 2, Introduction to Electrophilic Addition Reactions. These reactions that we're going to learn in this chapter are all electrophilic addition reactions to alkenes. And this is the first time that we're looking at an organic reaction. And typically when I teach a new organic reaction, I like to break down the name because all reaction names actually mean something, even though they sound like a bunch of gibberish. So we break it down into pieces in order to explain the overall meaning. So the first word, electrophilic, means we are going to involve an electrophile. If you do not have a species that can behave as an electrophile, this reaction will not move forward. Addition means exactly what it means even outside of organic chemistry. It means we are adding things together. 1 + 1 = 2. And what you'll see is that in the majority of these reactions, all of the atoms that are in the starting material and in the reagent end up in the product. So you can actually see the 1 + 1 = 2 situation happening across our chemical reagents. There's only one reaction where this isn't quite true, but it still does a 1 + 1 = 2 thing, and I'll show that to you. And then the last word is to alkenes. So this means that this chemistry is specific to alkenes and also alkynes, which are very similar, although most of these reactions we will not do with alkynes in this course. And this chemistry will not occur with other functional groups. So what happens here in this chapter with alkenes will not happen when we get to the benzene chapter. Even though we will see double bonds, they will not behave in the same way. And you would not see a carbonyl double bond behave in the way that we will see our molecules reacting in this chapter. So there are essentially 5 electrophilic addition reactions that we're going to look at in this chapter, and this is just kind of a rough run through. I did some color coding ahead of time in order to show you that whole idea of 1 + 1 = 2. So if you look at our alkene here, you'll notice that it has 6 carbons and 12 hydrogens. Over here on the other side, there are still 6 carbons and 12 hydrogens here. And then we are adding HX as our reagent. H and X end up in the product. So that's our 1 + 1 = 2 type of math that's happening here. And we're going to talk about the mechanism of this and how it happens, but I also want to point out that there's a pretty obvious trend here, and you'll notice it in the next several reactions as well. But that trend is that this molecule essentially breaks into 2 pieces, and one piece ends up over here and the other ends up over here. Now these are not reaction arrows. This is not how the chemistry occurs. This is not the mechanism. But I'm showing you that the reagent kind of has to split into 2 in order for this chemistry to occur. This first reaction, I didn't read the name out loud, is hydrohalogenation. This name comes from hydro for hydrogen, and then halogen because we have a halogen. X is the general shorthand for fluorine, chlorine, bromine, or iodine, although this chemistry does not occur with fluorine typically. You'll see it mostly with chlorine, bromine, and iodine because they are strong acids, and we actually need a strong acid in order to make this work. And then that last bit just tells you that a verb is occurring, basically. This next reaction is called hydration because we are adding water to our alkene. And the water ends up splitting into 2, and hydrogen ends up on one carbon, and the hydroxyl group ends up on the other. So the pattern is very, very similar to what we saw in the previous reaction. And then we have halogenation, which is where you are only adding halogens across the double bond. So one halogen ends up on one carbon of the alkene, and the other halogen ends up on the other carbon of the alkene. This next one is called hydroboration. This actually will not happen on its own in this chapter. This is chemistry that does occur, and we will actually use this reagent, which is called borane. We will see it as BH3 and as a complex with THF, which is a cyclic ether. But this is the chemistry that borane does And then we're going to very quickly replace the BH2 with something else so that this is not a product you're actually ever going to draw out. And then the last one is hydrogenation, which can also be called reduction. So this is hydrogenation because we are adding hydrogen across the double bond. So hydrogen and hydrogen, right? The reason it's also called reduction is because this is a situation where we took an alkene and turned it into an alkane. So we took a double bond and turned it into a single bond, and that is a type of reduction. In Gen Chem, you learn that reduction is a gain of electrons, but in organic chemistry, reduction often means either reducing the amount of oxygen in the molecule and or increasing the amount of hydrogen. So in this case, we took a molecule that had the formula C6H12 and turned it into a fully saturated C6H14. So our first two reactions that we're going to look at use the same general mechanism, and this is the kind of main idea of electrophilic addition, but then we'll learn that some of the other reactions we're going to look at kind of follow a slightly different path. So I've outlined it here, and I wrote out some steps, and then we're going to talk through this mechanism. So in the first step, the alkene attacks the proton. So this means that the alkene is acting, you can either say it's acting as a base and it's attacking an acid, boop, like that, or you could call it a nucleophile attacking an electrophile. Because again, this is electrophilic addition, we need an electrophile in order for our nucleophile to make the attack. Now with this arrow that I drew, I am saying that I'm going to make a bond from one of these carbon atoms to my hydrogen. And in this particular example, since this molecule is just ethene and it's symmetric, it doesn't matter which carbon you pick. We're going to look at when it does matter and how you make that decision. But in this example, it wouldn't matter. The hydrogen ends up on one of the carbons, and then the other carbon ends up positive. So carbocation is formed is the second step here. Now, anytime you make a carbocation, you have to ask yourself, is this the best I could do? And could I rearrange it? You cannot rearrange this one, but you want to get in the habit of asking yourself that. Now, the reason that this carbon is positive now is because it was neutral here when it was sharing these electrons with the other carbon. But we took those electrons and used them to make a bond to this hydrogen. So now the carbon on the left is the only carbon that has access to those electrons, and this carbon has lost them. So it is now positively charged. Now from this level, or this step, we have a nucleophile present in our reaction as well. In the reaction of HX, so a halogen acid, the H is used as the acid, and then X is our nucleophile. So at this point, we have a positive and we have a negative. And there is one rule that you'll hear me say a lot in organic chemistry, which is that minus likes plus. Anytime you have something negative and you have something positive, they are going to come together. So this nucleophile will have a lone pair, and it's going to make a bond to that carbon. So those electrons end up here. And this is how ultimately you end up with the hydrogen on one carbon and the nucleophile on the other.